is holomorphic in omega, and we have a ball. Let's put around Z0. Z or Z0. Let's just do Z. Contained within, I said omega. Then we actually have that F has a power series expansion. That F of Z actually Z0. Yeah, Z0. F of Z is equal to the sum from k equals 0 to infinity of AK Z minus Z0. Let's write that better. To the K, where these coefficients are the coefficients you would expect that you learn from just learning about Taylor expansions for functions just from R to R. Okay, and this is true for, I shouldn't say brackets, for any Z inside the ball around Z0, like this. Proof. Okay, so as I said before, we have now that there are infinitely many derivatives just as a consequence of the previous theorem. This is much stronger. Now we actually have that these things are analytic. We can expand them in a power series. So this is our domain, and we can fit some ball inside here. Then for anything inside this ball, then we can actually expand it out into this power series. Yeah? And the coefficients depend on the center of the ball, right? So if you want to consider something over here, then you still have that it's analytic, but then you have a different power series expansion. Yeah? They might turn out to be the same, but you don't necessarily know that just from this formula. Okay, so why is this true? Well, we have from Cauchy integral formula the following. Integral 2 pi I around the boundary of the ball Z0 of f of zeta, zeta minus z d zeta. This is Cauchy integral formula. Let's write it like this. And we're going to have zeta minus z0, z0 minus z d zeta, like this. So we're just adding and subtracting z0 at the bottom. Obviously that doesn't change anything. And let's write it like this. Let's factor out this. Let's factor out this z minus z0. Okay. So then we have, zeta minus z0. Let's factor out this guy. So then we're going to have 1 and then plus z0 minus z over zeta minus z0. Yeah, just doing some algebra here. And now let's write this as minus minus so that we can write z minus z0. So if we do that, then this becomes like this. Like this. Yeah? Cool. Now, what do we know? So let me do a bigger picture. this is our ball. This is Z0. We're integrating zeta around the outside, right? This is zeta. Yeah? And Z is something here. Z is something here, right? So this complex number, zeta minus Z0, has absolute value given by the radius of the ball. Yeah? And the radius of the ball is R. Yeah? Whereas the absolute value of Z minus Z0 is strictly smaller than that. Yeah? So this complex number here, Z minus Z0 over zeta minus Z0, is a complex number whose absolute value is less than 1. Are you all with me? Yeah? Give me a thumbs up if that makes sense to you. Yeah? So notice that for any zeta around the boundary of the ball, then absolute value of Z minus Z0 is strictly smaller than absolute value of zeta minus Z0. So therefore, the absolute value of this number, Z minus Z0 over zeta minus Z0, is strictly less than 1. Yeah? Now, recall this following formula for the geometric series, which follows in exactly the same. I mean, we already talked about it, we actually proved it, that if we take any complex number, let's call it W, we take the sum from k equals 0 to infinity, W to the k, where W is complex, that is 1 over 1 minus W for any W strictly less than 1. Yeah? This is a standard, this is, you learned this in series calculus 2. Exactly the same proof holds for complex numbers, and I think we even did it. Yeah? Cool. So, we can apply that to this thing here, because this is 1 over 1 minus a complex number strictly less than 1. Yeah? So, let me put it over here. So 1 over 1 minus Z minus Z0 over zeta minus Z0, yeah, is, by this formula, the sum from k equals 0 to infinity of Z minus Z0 over zeta minus Z0 to the power k. Yeah? Just applying the formula above. Yeah? Okay, so then we can put it directly into this thing. Let's call this thing star. So, star becomes that f of z is equal to 1 over 2 pi I, integral around the boundary of the ball of radius r around z0, and then f of zeta minus z0, and then this power series here. Because this power series makes sense, it's convergent, everything is, this is a meaningful function in every way. We've already learned it's holomorphic. We have all good stuff about this. We have nothing to be scared of when we write this. This is absolutely a true thing for any zeta around the boundary of the ball. This guy is all good. Okay, and we're integrating with respect to d zeta. Yeah? So, let's take a look at this. So this z minus z0, right, it's not involving zeta. Yeah? So what we'd like to do is to pull it out from the integral and then pull the sum out from the integral. In other words, swap the integral and the sum. And then what we'd have, it would be a power series in z minus z0. Yeah? That would give us a power series in z minus z0, which is the direction we want to head to. Yeah? But that's not a trivial thing because, again, this power series, it's defined as the limit of the partial sums, right? So what that would involve doing is swapping an integral and a limit. Yeah? And we've learned that we can do that when we have uniform convergence, yeah? Which means uniform convergence of this expression for every zeta around the boundary of the ball. Yeah? And what I will show, and what maybe some of you already anticipate, is that we do have this uniform convergence because this thing is a nice geometric series where this complex number is strictly below whatever. Strictly below the difference between this length and this length, or the ratio of this length to this length. Yeah? Actually, the difference between this length and this length. So you might anticipate that indeed we will be allowed to do that, but I'm going to explain that carefully. For the moment, though, I'm gonna anticipate that we're allowed to do this, and I'm going to show you the formula that we get is the formula that we want. Okay, so if we can swap the sum and the integral, i.e. pass a limit through the integral, then what would happen? Then we would have that f of z would be the sum from k equals 0 to infinity of z minus z0 to the k, and then we'd have the integral, let's put the 1 over 2 pi I over here, 1 over 2 pi I, the integral around the boundary of the ball, like this, of all of this stuff. It would be f of zeta, and then we have zeta minus z0, and then zeta minus z0 to the k, so it's zeta minus z0 to the k plus 1, like this. Yeah? The zeta. Yeah? Cool. Now, this is now our coefficients, right? If we're allowed to do this step, we now have a power series with these coefficients. But they're not the coefficients I claimed, or are they? Are these the coefficients I claimed? I claimed the coefficients were this. And now I have this. So has something gone wrong, or are these actually the same? Exactly, yeah. So by application of Cauchy integral formula for derivatives, this thing, yeah, I put this in blue, with the kth derivative, like this, is just k factorial times this expression. Yeah? 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 So this thing over k factorial is exactly this thing. Yeah? So that means we have exactly the theorem that we want. So this is the sum from k equals 0 to infinity of z minus z0 to the k, a k exactly the result that we want. Yeah? Cool. Are you all with me here? Before I raise the board, everybody happy? Yeah, give me a thumbs up if you are. If you're not, then, and you don't want to talk about it now, then I have office hour Monday from 11:10 to 12:10, and Wednesday 11:10 to 12:10 in my personal WebEx room, this room. Just show up there. Just turn up, ask me the questions. If this stuff is not making sense, it's only going to make less sense going forward, so just nail it down. Watch the video over, write down what is unclear to you, make a note specifically what's unclear to you, then come to my office hour and ask me about it, okay? Don't let this thing just drift in some kind of not clear place for you, hoping that later it's all going to fit into place. The exact opposite will happen. If you have areas of misunderstanding, they will expand as we go forward. So close them down as quickly as possible. Watch the video, make notes, come to my office hour. You will understand this, I promise you. Cool. So we want to pass through this limit. Yeah, we want to pass through this limit. We want it to be uniform with respect to, well, let me say that better. So this thing is the following partial sum, right? This is the limit as n goes to infinity of this partial sum, right? That's the meaning of this infinite sum, right? So this partial sum here is a limit, and it depends on zeta, right? Depends on zeta, yeah? So we can write this thing, so we're going to write that, we're going to write Sn of zeta. So z we're just taking as fixed, we take it inside the ball, it's not moving, we're just going to establish this for our particular choice of z. So we write this thing is this partial sum, the sum from k equals 0 up to n of z minus z0 to the k over zeta minus the k plus 1 times f of zeta, like this. Yeah? We're going to write this as this partial sum, and what we want is to take this limit out. So this is 2 pi I, and then this is the integral around the boundary of the ball, like this, of the limit as zeta, the limit as n goes to infinity of Sn of zeta d zeta. Yeah? Now, if we just had Sn here, right, then it's just a finite sum, and then we can swap the summation and the integral. That would be fine. Yeah? So the real issue is passing the limit out. Yeah? Yeah? But we've learned that if for all zeta living around the boundary of this ball, so this is our ball, right? Radius r, and zeta lives right here. We've learned that as we consider all these zeta around the boundary of the ball, if this expression uniformly converges to its limit, which is this infinite sum, yeah, then we can do it. Then we can actually do it. That's what we learned, that's what we did last time. So when we have a sequence of functions, yeah, let me put it over here. So if Fn tends to f uniformly on gamma, yeah, then the integral Fn dz, the limit of this as n goes to infinity over gamma, is just this thing. This is this little calculation, and it just follows from taking the absolute value signs inside, right? So uniform convergence allows us to pass the limit through the integral. Yeah? Is this coming back? Yeah? That's how we proved the Cauchy integral formula for the derivatives, right? That was the last step we had to do. Yeah? So all we need for this to work is that this thing, the partial sum, this expression over here, has to tend uniformly, independent of the choice of zeta, to the limiting function, which is the infinite sum right here. Are you with me, everybody? Everybody happy? Cool. All right, so let's take a look. So let me write that in words. So to pass the limit through the integral, we just need, so I'm going to write S infinity for the actual infinite sum, that Sn tends to S infinity uniformly on on the boundary of the ball, like this. Cool. Now, let's see what S infinity minus Sn looks like. So we're going to define the remainder term Rn like this. We're going to define it to be S infinity, the entire sum. So actually, let's make sure we are clear that all this stuff depends on zeta, because it has to be independent of zeta. It has to be uniform in zeta. So Rn of zeta, we're going to define it to be the infinite sum minus the partial sum. Yeah? And then from this expression, what's that? That is the sum from k is equal to n plus 1 to infinity of all of this stuff. Let's write it like this. Z minus Z0 over zeta minus Z to the k, and let's write this, f of zeta over zeta minus Z. 1 second. We had, it's not zeta minus Z, it's, yeah. There we go. Thank you. Zeta minus Z naught, like this. Cool. So this is our expression like this. Yeah? This means that the remainder is exactly this. Yeah? Cool. So let's be very, very careful, because this itself is defined as an infinite sum. So let's define this. N, and let's put an M. So we'll take the finite sum like this. Yeah? Where M is bigger than n. Then we can estimate this thing, right? So the absolute value of our m n of zeta is just, we're going to put the absolute values through this thing. It's a finite sum. We don't have to worry about taking absolute values through it because there's no limit involved. It's now a finite sum. So then this is less than, I mean, it's going to be fine because absolute value is convergent and the sum's convergent, but that's what we're about to show. So I don't want to muddy the water here. And then the absolute value of this thing, z minus z0 over zeta minus z0, like this, to the k, and then the absolute value of this thing, and then this thing, absolute value. Okay. This thing is, so z is fixed, zeta is going round the circle, right? So here is z, maybe, yeah? Yeah, I mean, z can be anywhere. It can be really, really close to the boundary here, yeah? But this number, yeah, is always less than some particular number less than 1. We have that z minus z0 is less than r minus something, so let's write that down. Z minus z0 is less than, say, 1 minus delta times r for some delta. It's just true, yeah? And then zeta minus z0 is just equal to r, so this thing here is less than just 1 minus delta to the k. Yeah? So then this thing is less than the sum from k equals n plus 1 to infinity, just 1 minus delta to the k. Yeah? This thing here, it's just equal to r itself. Let's put it here. So we're summing with respect to k. And this thing is less than the supremum of the function f on the boundary of the ball. So the supremum of the function on the boundary of the ball of radius z0, like this. Yeah? Everybody with me? Yeah? So you can just pull out this thing and this thing. So then we have the supremum of the boundary of the ball, z0. We have f, and then let's divide it by r, right? And then we have this thing. We have the sum from k is equal to n plus 1 to infinity of 1 minus delta to the k, yeah? And what's this thing? This is just the supremum over the boundary of the ball of z0 of this over r, like this. And then this thing is 1 minus delta to the n plus 1 over 1 minus delta, so like this. Yeah? So this thing here, by our geometric series stuff that we know from Calc 2, is just equal to this. Yeah? Cool. So for sure, this thing is going to 0 as n goes to infinity, because 1 minus delta is going down to 0 as we take higher and higher powers. Yeah? And it doesn't notice anything about zeta, right? This is independent of whatever zeta is. Yeah? Yeah? Cool. All right, good. So that means that we can actually consider a Cauchy sequence like this. So for any fixed zeta, so Sn of this forms a Cauchy sequence, because this is exactly estimating the difference between Sm and Sn. Yeah? And we know it's going down to 0 as m and n goes to infinity. So this is a Cauchy sequence, and it's going to converge to its actual limit, which is going to be S infinity. So this thing converges to S of infinity of zeta. Yeah? And infinity n of zeta equals the limit. So the absolute value of signs like this equals the limit as m goes to infinity of m n of zeta, just by definition. Yeah? And the absolute value is continuous, right? And we have that this thing is indeed converging to this thing because of this estimate. So this is equal to the limit as m goes to infinity of this guy. And this guy is always less than this particular estimate, some constant times 1 minus delta to the n plus 1. So I'm running out of space, so I'm putting everything here, which I'm putting everything which isn't the 1 minus delta to the n plus 1 just as a constant, because it's not moving with respect to n. Okay. So that's what we want, because we have that this thing, which is the remainder, which is the difference between the partial sum and the actual infinite sum, is uniformly bounded. This doesn't depend on zeta. This doesn't depend on zeta. Yeah? This is independent of zeta. So we can just guarantee that for any zeta, this thing is as small as we like by taking n to be large enough. Yeah? So we do indeed have that the partial sums uniformly converge to the actual sum. Yeah? And this allows us to do this exchange, to take this limit outside this integral, and the last equation we wrote on the previous board gives exactly the expansion. So we've proved the Taylor expansion for holomorphic functions, and it followed really easily from just Cauchy integral formula. Okay, so just as before, the actual formula is really easy to deduce. We just have to do a little bit of work to make sure that we can swap the limits of the integral sign. Just exactly the same issue as with respect to deducing the Cauchy integral formula for derivatives. The formula itself was just natural, just consequence of the algebra, but making sure that we could pass through the limit was a little bit of extra thought. So we have this. We have that holomorphic functions are actually analytic. They have a power series expansion. around every single point in the domain, right? And once you have a power series, then it has a radius of convergence. It might be bigger than the actual domain. Yeah? So sometimes we'll have a function which is defined on some domain. We'll have a power series expansion, and we can actually define it outside of its domain. And that's another topic that we will discuss going forward.